Hi, and welcome to the 40th day of Just Start Programming, the Rust programming language. Today we will continue building a multi-threaded web server, which is still part of the book. And if we still have time, we can go through the appendix section of the book just to be familiar and know that there are those things. So let's do this live in one take, no shortcuts, no secrets. So let's just start programming. All right, so 40th day. That's been a long journey. And today we'll continue where we left off last time. So I think we were somewhere here where we need to refactor the code and use a threading mechanism for our web server. So let's backtrack a little bit and see what else we need to do. Right, so here in main RS handle connection, we have this match where we are using an arm to change. Okay, I think this was from the previous one where we don't want to repeat things. So whether we get hello or we return hello or 404 is based on this um, uh, response or no request. Let's just check from the code once again if we have it. Yeah, it's here. And then let's come back here. So threading, spawning a thread for each request. Okay, so here we are using thread spawn from main. Let's check our main. Thread spawn. Okay, so it looks a bit different. So here we are using thread pool. Okay, so I think we have already moved on to implementing thread pool new size 4. Okay, and we have execute. Okay, but this part here won't compile. Undeclared type thread pool. So thread pool new. So I think in library thread pool. Yep, so we have new function. Then struct thread pool, hello thread pool. So this is in main. In main we had the hello thread pool. And then here, okay, so function new, it returns thread pool. Okay, here, cargo check. I don't think we have any errors. Compilation error. Okay, so it looks clean. Here. We'll define the execute method on thread pool to take a closure as parameter. So this is in the library, thread pool library. So let's come back to thread pool library. Execute. Okay, so F, we only have fn1s. fn1s. Okay, so I think we are here. Okay, so let's read what was the explanation. We still use the parenthesis after fn1s because this fn1s represents a closure that takes no parameters and returns a unit type. Just like function definitions, the return type can be omitted from the signature, but even if you have no parameters, you still need the parenthesis. Okay, so it's the pattern. We still need the parenthesis. This is the simplest implementation of the execute method. It does nothing, but we're only trying to make our code compile. So there's no concrete implementation yet. It does nothing. It's just to make it compile. So let's see, terminal. Okay. Cargo check. Warnings. But it looks fine. So dev profile and optimize as debugging info is what is expected here. Okay, so there's always a difference between the book and the actual. So that's why it helps if you have somebody together with you. Yeah, because there are certain things that are omitted as well. So this is as realistic as it can get. You get to see warning messages here. Yeah, because over here we are doing it a bit different also. A little bit different. Not exactly the same as the one in the book. Okay. Oh, I think I remember this part the other day. What would be different here if we were going to execute a future instead of closure? Because the implementation is the closure approach and not the future. But let's follow the book. All right, validating the number of threads in new. Okay. So we aren't doing anything with parameters to new. Let's check again. New, yeah, we're just returning thread pool. But in this case, let's implement the bodies of these functions with the behavior we want. To start, let's think about new. Earlier, we chose an unsigned type for size parameter because a pool with a negative number of threads makes no sense. However, a pool with 0 threads also makes no sense. Yet 0 is perfectly valid new size. We'll add code to check that size is greater than 0 before we return thread pool instance, and have the program panic if it receives 0 using assert. Okay. Assert, I think this checks if it's false. Okay, so false, it will panic. So I think this is the only change that we need to do. Let's copy it here. Assert. So we can also take a look. Assert asserts that a Boolean expression is true at runtime. Yeah, so it will invoke panic if otherwise. Okay. We've also added some documentation for our thread pool. It's the documentation. Okay, this part here is the documentation. Thread pool. You can just insert it here. Looks like a comment with the triple slash, which means goes into the documentation. How do we generate the documentation? Yeah, so here, cargo doc open. Cargo doc open. So let's open up our terminal. Yeah, so cargo doc open. You can do this from the terminal. Paste. Oops. Building. Opening. Yep. Okay, thread pool. It says create a new thread pool. The size is the number of threads in the pool. Panics. The new function will panic if the size is 0. Description here. Panics. Okay. Nice. Close that. This one we don't need to do. Just come back to here. Okay, so instead of adding the assert macro, as we've done here, we could change new into build and return a result like we did with config build. In the IO project in this thing 12-9, but we've decided in this case that trying to create a thread pool without any threads should be an unrecoverable error. Unrecoverable, so it means the application will just stop. If you're feeling ambitious, try to write a function named build with the following signature to compare with the new function. If you're feeling ambitious, it's here. Result thread pool creation error. Creating space to store the threads. Okay, we'll skip this for now. Creating space to store the threads. Now that we have a way to know we have a valid number of threads to store in the pool, we can create those threads and store them in thread pool struct before returning the struct. How do we store a thread? Let's take another look at the thread spawn signature. Thread spawn, so you have fsend or tsend static. Then you have join handle. Okay. The spawn function returns a join handle t, where t is the type that the closure returns. Let's try using join handle 2 and see what happens. In our case, the closures we're passing to the thread pool will handle the connection and not return anything. So t will be the unit type parenthesis. The code in listing 21-14 will compile but doesn't create any threads yet. We've changed the definition of thread pool to hold a vector of thread join handle instances, initialize the vector with a capacity of size, set up a for loop that will run some code to create threads, and return a thread pool. Okay, so going back to lib.rs, okay, so we have a vector of threads with this join handle, and the thread pool, so aside from checking if it's more than 0, there's some fact with capacity size, a mutable thread. Okay, let's copy this one first. Thread pool. So no, that's the struct thread pool. Okay. Since we're using thread, we need to add in the import. Okay, and then we need this part. Okay, then here, what was the error? Threads. Okay, so here, create some threads and store them in the vector. So we're not creating threads yet here. It says it won't compile. Everything looks fine. Why it won't compile? We brought std thread into scope in the library creates because we're using thread join handle as a type of the items in vector in thread pool. Once a valid size is received, our thread pool creates a new vector that can hold size items. The with capacity function performs the same task as the vect new, but with an important difference. It pre-allocates space in the vector. Because we know we need to store size elements in the vector, doing this allocation up front is slightly more efficient than using vec new. Okay, so instead of vec new, with capacity is used, which resizes itself as elements are inserted. Okay, so this is the thing that differentiates it with new. Wonder if we can see some documentation here. Okay, constructs a new empty vector with at least the specified capacity. At least, okay, so if we specify size, the vector will be able to hold at least capacity elements without reallocating. This method is allowed to allocate for more elements than capacity. If capacity is 0, the vector will not allocate. It is important to note that although the return vector has the minimum capacity specified, the vector will have a 0 length. For an explanation of the difference between length and capacity, okay. Okay, so this one is more suitable. And then here, and you run cargo check again, it should succeed. It should succeed. Cargo check. So let's open a new terminal here again. Cargo check. Okay. Looks fine. So you can do that from the terminal, from our IDE, or you can do it from here. Check. Then a worker struck responsible for sending code from the thread pool to a thread. We left a comment in the for loop. This one, it's not implemented yet. Regarding the creation of threads, here we'll look at how we actually create threads. The standard library provides a thread spawn as a way to create threads, and thread spawn expects to get some code the thread should run as soon as the thread is created. However, in our case, we want to create the threads and have them wait for code that we'll send later. Okay. Standard library's implementation of threads doesn't include any way to do that. Okay, so we have to implement it manually. We'll implement this behavior by introducing a new data structure between thread pool and the threads that will manage this new behavior. We'll call this data structure worker, which is a common term in pooling implementations. The worker picks up code that needs to be run and runs a code in the worker's thread. Okay, so it sounded like there's another thread here. Think of people working in the kitchen at a restaurant. The workers wait until orders come in from customers, and then they're responsible for taking those orders and fulfilling them. Instead of storing a vector of join handle instances in the thread pool, we'll store instances of the worker struct. Each worker will store a single join handle instance. Then we'll implement a method on worker that will take a closure of code to run and send it to the already running thread for execution. We'll also give each worker an ID. Each worker will have an ID so we can distinguish between the different instances of worker in the pool when logging or debugging. Here's the new process that will happen when we create a thread pool. We'll implement a code that sends the closure to the thread after we have workers set up in this way. Okay, first step, we define a worker struct that holds an ID and join handle. Okay, so worker struct, it means we'll have another struct here. Worker struct. Let's see where is it? Here, worker struct. Change thread pool to hold a vector of worker instances. Okay, change. Okay, so here vect is now holding the worker. Okay, so in the previous code, it's thread join handle. Okay, so we're going to change that as well. Define a worker new function. So worker new, that would be struct implementation. Okay, so worker struct impl worker. Okay, then we have the function new. What does it say? Takes an ID number and returns a worker instance that holds the ID and thread spawn with any empty closure. So ID, then thread spawn, and you have the closure empty. Okay, but that one will return a worker with an ID and the thread. Okay, so it will just return the new thread with an ID, which we will specify here. In thread pool new, use the for loop counter to generate an ID. Create a new worker with that ID and store the worker in the vector. So thread pool new, use for loop to generate an ID. Okay, thread pool new, coming back to the for loop, which was, in our case, it was not implemented yet. So the workers, okay, because the workers are returned here from vec with capacity, so it's a vector, so we are pushing it. Yeah, so we are inserting, it's like you're inserting in this vector. So we have worker. Okay, so this is a new instance of a worker with ID. ID in 0, so it starts with 0 to size, depending on what size you specify here. Okay. And store the worker in the vector. Okay, so the worker is stored in the vector. So push. But which workers? These workers. No, these workers. But then you're passing it inside the thread pool for workers. Okay, so you have one thread pool here once you call new. Okay. If you're up for a challenge, try implementing these changes on your own before looking at the code in listing. Ready. Okay, so let's try that one. Let's see if we can remember. I don't think I have that good memory. So I think the first step was, okay, we create a struct, public struct workers. Then here we change this to workers instead of this. Workers. Okay, then here, of course, you need to they're not threads anymore. So maybe we comment this out and change threads to workers. Here, what was that? Is it workers? Workers. Like this. No, should be vect. This is not threads, but workers. Thread with workers. Okay. What did we miss? Okay, workers work. Push the workers. But in the worker, we need to implement new. Okay, so new worker where we return. This one we forgot to do this. Okay, ID new size and plus the other one. This should be how was it called? Thread. Semicolon because this is a struct worker. We have a comma at the end. I wonder if we remove it, if it's okay. Okay. Okay, so workers. And then we need to implement workers with a new function. So struct pl workers. And here function new. It was required for workers, so you need an ID. This one will return. It will return a vector of workers. Was it that? Okay, let's do that for now. Let's change it later if it's wrong. Okay, so I'm going to cheat a little bit. Oh, it's just worker. Okay, worker. It's just worker. Okay. It's not workers. It's just worker. Worker. One is actually thread. This is worker, then here. Workers. So it should be worker. Okay, and here. So it should return worker. And then you have ID and thread. Net thread. That's it. So thread spawn. Spawn. And you have a closure that is empty. The thread. What is wrong with thread? Okay. It's not a vector. Thread join. There. Then here we have workers dot push, because we are pushing into a vector. We have worker dot new with size. Okay. Oops. What's wrong with this? No, it is workers. Not, it's not a dot, but this one. Okay. Have we completed it? Workers. What is wrong with this? I can't find type. Oh, it's not workers, it's worker. Worker. Yeah. Worker. Okay, workers. Workers was not used. Workers were never used. Okay. And I miss anything. Workers back worker. Workers back worker. Math workers where we're creating a vec with capacity. Let math workers vec with capacity size for okay, so this one should be ID. So we're creating workers with an ID, then we are storing it in a vector. Okay, does it look complete now? I think the indentation is a bit off here. Okay. Okay, so it looks complete now. Let's come back to the documentation. Yep, so we've changed the name of the field on thread pool from threads to worker. Thread pool. That's it. Thread pool, threads to workers. Okay. Because it's now holding worker instances instead of join handle instances. We use the counter in the for loop as an argument to worker new. Okay, because of this ID argument new. Okay. And we store each new worker in a vector named workers. Vector named workers. External code like our server in source main RS doesn't need to know the implementation details regarding using a worker struct within thread pool, so we make the worker struct in its new function private. So we can remove pub. Okay, this is without pub, it's private by default. The worker new function uses the ID we give it and stores a join handle instance that is created by spawning a new thread using an id closure. Okay, so it's this part, id. Keep the id here, and the thread is this one, where you have a closure. Okay, note my mouse was jumping again. Let me see, where was it? Okay, here. Note if the operating system can create a thread because there aren't enough system resources, the thread spawn will panic. That will cause our whole server to panic even though the creation of some threads might succeed. For simplicity's sake, this behavior is fine, but in a production thread pool implementation, you'd likely want to use std thread builder and its spawn method that returns result instead. This code will compile and will store the number of worker instances we specified as an argument to thread pool new. But we're still not processing the closure that we get in execute. Let's look at how to do that next. Okay, so we're not going to run it yet. Sending requests to threads via channels. The next problem we'll tackle is that the closures given to thread spawn do absolutely nothing. Currently, we get the closure we want to execute in the execute method, but we need to give thread spawn a closure to run when we create each worker during the creation of the thread pool. We want the worker structs that we just created to fetch the code to run from a queue held in the thread pool and send that code to its thread to run. The channels we'll learn about in chapter 16, a simple way to communicate between two threads would be perfect for this use case. We'll use a channel to function as a queue of jobs, and execute will send a job from thread pool to the worker instances, which will send the job to its thread. Here's the plan. The thread pool will create a channel and hold on to the sender. Each worker will hold on to the receiver. We'll create a new job struct that will hold the closures we want to send down the channel. The execute method will send the job it wants to execute through the sender. In its thread, the worker will loop over its receiver and execute the closures of any jobs it receives. Let's start by creating a channel in thread pool new and holding the sender in the thread pool instance as shown in 21-16. The job struct doesn't hold anything for now, but will be the type of item we're sending down the channel. Okay, so what has changed here? NPSC mainly for the channel. Okay, so you'll have a sender here. So let's start with this implementation. Worker. Then, yeah, we need the library. And then the job. Sender job, okay. Job, that one is a struct. Then We're going to create a channel, PSC channel, sender and receiver. Okay, so let's add it here. And okay, no changes here. Then in the thread pool, so we have workers and sender, we add in the sender. Workers. Okay. Okay. In the thread pool new, we create our new channel and have the pool in the pool hold the sender. This will successfully compile. Let's try passing a receiver of the channel into each worker as the thread pool creates the channel. We know we want to use the receiver in the thread that the worker instance has spawned, so we'll reference the receiver parameter in the closure. Okay, so here it says it won't compile yet. So let's take a look at the code snippet. So we have already done this. We've defined a channel where you have a tuple of sender and receiver. And then the thread pool will hold the workers and then the sender. In worker, you have, okay, so you should accept receiver as the parameter. Let me copy that. It would still return worker, and here thread spawn in the tuple. It will spawn our receiver, and then this one will not change. Okay. Okay, so we'll add in another parameter here. The implementation here will be the receiver. Let thread spawn, let thread spawn receiver. Yeah, thread. Okay. So it says it won't compile yet because of this. So two arguments, ID and receiver. Where do we get the receiver? Receiver from this one. Because we added the parameter, so we update this one as well. Receiver. Receiver job. Sender job. Value moved here. Okay. Yeah, so the borrow checker is complaining. We made some small and straightforward changes. We passed the receiver into worker new, because we have changed the number of parameters. Worker new, size and receiver. Size and receiver. Okay, size is the ID. When you try to check the code, you get this error. The code is trying to pass receiver to multiple worker instances. This won't work. As you will recall from chapter 16, the channel implementation that Rust provides is multiple producer but single consumer. This means we can't just clone the consuming end of the channel to fix this code. We also don't want to send a message multiple times to multiple consumers. We want one list of messages with multiple worker instances such that each message gets processed once. Additionally, taking a job off the channel queue involves mutating the receiver, so the threads needs a safe way to share and modify a receiver. Otherwise, we might get race conditions as covered in chapter 16. Recall the thread-safe smart pointers, chapter 16, to share ownership across multiple threads and allow threads to mutate the value. We need to use ARC, not ARC, but ARC. Synchronous, what was this? Reference counter. That's what it means. Then you have mutex. Okay, mutex. Another trait, perhaps. The archetype will let multiple worker instances own the receiver, and mutex will ensure that only one worker gets a job from the receiver at a time. Okay, so here mutex will ensure. Okay, so it's like mutex will have that guarantee that there's only one worker that gets a job from the receiver at a time. Okay, so the listing 21-18 shows the changes we need to make. Okay, so it mentions arc and mutex, so that will be added in the import. Let's change here. Okay, so receiver, yeah, so this is the new one. So we'll edit here, receiver. Or so we need to import this one also, import. How does it look? Sync. Oh, this one looks a bit different. Yeah. Okay. Okay, so we have done that. Receiver here. Arguments to these functions are incorrect. Okay, let's see. Worker new, then you have ID. Okay, so it's wrapping the receiver. Arc clone. Arc new receiver. Okay, okay. So this receiver is now arc, and we are cloning it. Okay. So here the reference to. Oops. Reference to the receiver. Okay, receiver. Then we will do an arc clone. Clone self receiver. Okay, so there's still an error. Arguments to this function are incorrect. Worker new ID receiver. Worker new ID. Okay, worker new ID receiver. At receiver. Okay, because here it has changed also to this one. So come back here, receiver. Let's just comment on that one. Receiver is arc, new text. What is it? MPSC as receiver job. Looks very complex. That definitely looks very complex. You have a job. Initially, you have a receiver that will contain a job enclosed in a mutex to ensure that it will only call one receiver at a time. Then a synchronous reference counter. Yeah, so let's continue. In thread pool new, we put the receiver in an arc and a mutex for each new worker. We clone the arc to bump the reference count so the worker instances can share ownership of the receiver. With these changes, the code compiles. We're getting there. Implementing the execute method. Let's finally implement the execute method on thread pool. We'll also change job from a struct to a type alias for a trait object that holds the type of closure that execute receives. As discussed in creating type synonyms with type aliases in chapter 20, type aliases allow us to make long types shorter for ease of use. Okay. What has changed here? Thread pool, execute, fn1s, box. Okay, so job is this one. Aliases. So thread pool. We'll insert it here. Then thread pool. Function execute. Fn1 send plus static. Okay, we add this one. Okay, so job mismatch. What was the issue? Self sender execute. Okay, execute self f where fn1 send static. Let job box new f self sender send job unwrap. Type job. The type job is over here. Okay, let's finally implement the execute. We also change job from struct to a type alias. Okay, so it means get this out. Okay, so there. Okay, so it's okay now. So the instead of struct, there's a type alias where job means a box dynamic fn once send static. Even this one already looks very complex. After creating a new job instance, using the closure we get in execute, using the closure we get in execute, I think it's referring to this part. We send the job down the sending end of the channel. We're calling unwrap on the end. Okay, so here we're sending it to the channel. We're calling unwrap on send for the case that sending fails. Yeah, so we have error handling here. This might happen if, for example, we stop all our threads from executing, meaning the receiving end has stopped receiving new messages. At the moment, we can't stop our threads from executing. Our threads continue executing as long as the pool exists. The reason we use unwrap is that we know the failure case won't happen, but the compiler doesn't know that. But we're not quite done yet. In the worker, our closure being passed to the thread spawn still only references the receiving end of the channel. Instead, we need the closure to loop forever, asking the receiving end of the channel for a job and running the job when it gets one. Let's make the change shown in listing 21-20 to worker new. Worker new spawn. Okay, so now you have move here. And then you have a loop, receiver, lock, unwrap, receive, unwrap. What was that? Okay, so instead we need the closure to loop forever. So we have a loop here. Condition asking the receiving end of the channel for a job and running the job when it gets one. Running the job when it gets one. Okay. So what do we need to do here? It is inside worker new. Worker new. Okay, so receiver. Of course, in the closure, we need to insert move first. And here it says there's a loop. And then inside the loop, that job one something, then we execute the job. Job. Okay, so receiver log. Oops. Is it dot? Yeah, dot unwrap dot receive dot unwrap. Okay, job receiver lock unwrap receive unwrap, and then we okay, so we can add this as well. Okay, and let's continue. Here we first call lock on the receiver to acquire the mutex. Okay, so lock is to acquire the mutex. And then we call unwrap to panic on any errors. So that's the first unwrap. Acquiring a lock might fail if the mutex is in a poison state. This is something new. Okay. The mutex is in poison state, which can happen if some other thread panicked, holding the lock rather than releasing the lock. In this situation, calling unwrap to have this thread panic is the correct action to take. Feel free to change this unwrap to unexpect with an error message that is meaningful to you. If we get a lock on the mutex, we call receive to receive a job. Okay, so receive a job from the channel. A final unwrap moves past any errors here as well, which might occur if the thread holding the sender has shut down. Similar to how send method returns error if the receiver shut down. Okay, so I didn't know that lock here is for mutex. This is definitely something new. How about if we I just want to try if this will compile. I don't want the lock. I just want to receive. Oh, complaints. No method received found for struct arc mutex. Method not found. Okay, so try lock. Okay, you have lock and try lock. Oh, okay, because it's a mutex. Okay, so yeah, it's a mutex. I was wrong. Okay. Call to receive blocks. So if there's no job yet, the current thread will wait until a job becomes available. The mutex T ensures that only one worker thread at a time is trying to request a job. Our thread pool is now in a working state. Give it a cargo run and make some request. Cargo run and make some request. Needs to be done here. Just cargo run. Okay. Alright, so let's do it. Let's do it from here. Go run. How come we don't see this worker? What do we need to do? Did we miss anything? New. Okay, thread pool new. He's calling thread pool new. Thread pool. Thread pool new. We have 4. Okay. 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 Let's do it again. We run from here. Alright, and then here, thread pool. Okay. So, from Rust. But worker 4 got a job executing. Let's duplicate. Sleep. We still have sleep. Kate. Worker 4 got the job. Worker 4. Why is it always worker 4? Worker 0 got a job. Worker 2 got a job executing. Why is it always worker 4 here? Let me close this one. Still worker 4. There are never more than 4 threads created, so our system won't get overloaded if the server receives a lot of requests. If we make requests to sleep, the server will be able to serve other requests by having another thread run them. Note, if you open sleep in multiple browser windows simultaneously, they might load one at a time in 5-second intervals. Some browsers execute multiple instances of the same request sequentially for caching reasons. This limitation is not caused by our web server. This is a good time to pause and consider how the code would be different if we were using features instead of a closure for the work to be done. What types would change? How would the method signatures be different, if at all? What parts of the code would stay the same? After learning about the while-let loop in chapters 17 and 18, you might be wondering why we didn't write the worker thread code as shown in 21-21. While-let, okay, job, receiver, unlock, receive. This code compiles and runs, but doesn't result in the desired threading behavior. A slow request will still cause other requests to wait to be processed. The reason is somewhat subtle. The mutex struct has no public unlock method because the ownership of the lock is based on the lifetime of the mutex guard within the lock result that the lock method returns. At compile time, the borrow checker can then enforce the rule that a resource guarded by a mutex cannot be accessed unless we hold the lock. However, this implementation can also result in the lock being held longer than intended if we aren't mindful of the lifetime of the mutex guard. Okay, so maybe we need to look into these things. Mutex guard also results. Mutex guard. The code listing in 21-20 that uses let job receive works because let any temporary values used in the expression on the right hand side of the equal sign are immediately dropped when let statement ends. However, while let and if let and match does not drop temporary values until the end of the associated block. Okay, so because you have a block here, as compared to this one, the lock remains held for the duration of the call to job. Meaning the other worker instances cannot receive jobs. Yeah, but I'm still not sure why this is for. Let me just take a look. What's the print line we had? Worker ID. Okay, worker ID. Worker new. Worker new. New ID. It doesn't have any explanation also why I'm running it. Okay, this is just warnings. How to simulate that one? Terminal. We close this. Cargo run. Hello. I still don't know why it's always 4. ID is based on worker new. Okay, ID is based on worker new. ID, no, new, so if you put 4, that is the size. Okay, so that is from 0 to 4. Worker push. id let mat workers. Okay, so it's here vec with capacity size. Workers that push worker new id. Workers that push worker new id. id. Okay. Okay. So it should be id. Okay. That one. I think that's the culprit. Let's see now. And hello. Hello. Okay. Okay. So. Okay. So that solves it. All right. Okay. Then we need this graceful shutdown because we're just doing a control C. Okay, so we got some warnings about workers ID and thread fields that we're not using in a direct way. That reminds us we're not cleaning up anything. Okay, next we'll implement the drop trait to call a join at each of the threads in the pool so they can finish the request they're working on before closing. Then we'll implement a way to tell the threads they should stop accepting new requests and shut down. To see this code in action, we'll modify our server to accept only 2 requests before gracefully shutting down its thread. One thing to notice as we go, none of this affects the parts of the code that handle executing the closures. So everything here would be just the same if we were using a thread pool for an async runtime. Okay, implementing the drop trait on thread pool. Let's start with implementing drop in our thread pool when the pool is dropped. Our threads should all join to make sure they finish their work. First attempt at a drop implementation. Okay, so this will not compile yet. What is here? Okay, implementing the drop trait in librs for thread pool. Okay, so we can just copy this. Come back to librs. Where's our thread pool? Thread pool is here. So we can implement drop. Okay. And of course it will complain. Execute and here. Oh, there's so many errors. Why? New is not a member of trait drop. Okay. Mm-hmm. Okay, so it will not compile yet. First, we look through each of the thread pool workers. We use at mat. No, at mat, but in reference to mat, ampersand mat. For this, because self is a mutable reference. And we also need to be able to mutate worker. For each worker, we print a message saying that this particular worker instance is shutting down. And then we call join, the worker thread join, on that worker instance thread. If the call to join fails, so unwrap to make Rust panic and go into ungraceful shutdown. So cargo check, it will not compile. Worker thread move due to this method call. Okay. The error tells us we can't call join because we only have a mutable borrow after each worker, and join takes ownership of its argument. To solve this issue, we need to move the thread out of the worker instance that owns the thread. So join can consume the thread. One way to do this is by taking the same approach we did in listing 18-15. If worker held an option thread, we could call the take method on the option to move the value out of some. Okay, option will have some and none variant and leave a non-variant in its place. In other words, a worker that is running will have some variant in thread, and when we wanted to clean up a worker, we'd replace some with none, so the worker wouldn't have a thread to run. However, the only time this would come up would be when dropping the worker. In exchange, we'd have to deal with an option thread join handle anywhere we access worker.thread. Idiomatic Rust uses option quite a bit, but when you find yourself wrapping something you know will always be present in option as a workaround like this, it's a good idea to look for alternative approaches. They can make your code cleaner and less error-prone. In this case, a better alternative exists. Vec drain method. Okay, so this is new once again. It accepts a range parameter to specify which items to remove from vec and returns an iterator of those items. Passing the range syntax will remove every value from the vec. So we need to update the thread pull drop implementation like this. Okay, so the implementation of drop is changed to for worker in self workers drain. Okay, so let me copy this one. So it means this one will compile. Let's compare to this one. Workers drain. Yeah, drain is from vector. Okay. This resolves the compiler error and does not require any other changes to our code. Okay, so good choice. Where are we? Signaling to the threads to stop listening for jobs. With all the changes we've made, our code compiles without any warnings. However, the bad news is that this code doesn't function the way we want it to yet. The key is the logic in the closures run by the threads of the worker instances. The moment we call join, but that won't shut down the threads because the loop forever looking for jobs. We try to drop our thread pool with our current implementation of drop. The main thread will block forever, waiting for the first thread to finish. To fix this problem, we need to change the thread pool drop implementation and then a change in the worker loop. Okay, so first we'll change the thread pool drop implementation to explicitly drop the sender before waiting for threads to finish. Listing 21-23 shows the changes to thread pool to explicitly drop sender. Unlike with the thread, here we do need to use an option to be able to move sender out. Oh, previously we were avoiding option, so that's why drain was implemented instead here. Okay, but now we're back to option. To be able to move sender out of thread pool with option take. So what are the changes? Okay, sender is wrapped in option. Okay, so let's change this part first. Come back to thread pool. We comment this out. Then thread pool workers sender, some sender. Okay, so this one will have an error. Then this one has to change. Execute sender box new. Oh, okay, so as reference. And then where's the take? Option take. Sender out of thread pool with option take. Option take. Here. Drain worker ID, shutting down worker ID, worker thread join unwrap. Okay. Unwrap. Then what else needs to be done? Dropping sender closes the channel. Dropping sender closes the channel, which indicates no more messages will be sent. When that happens, all calls to the receive and that worker instances doing the infinite loop will return an error. We change the worker loop gracefully, exit the loop in that case, which means the threads will finish when The thread loop drop implementation calls join on them. Okay, so what needs to be changed here? Lock, unwrap, receive. So instead of unwrap, we have a match. Okay. Receiver, lock, unwrap, receive. Lock, unwrap, receive. Let's comment that out, and here, let's remove unwrap. Then here, let's put this job. Now message is where? Message, touch message. Okay, that is message. This is message. I'm running a little bit of overtime. I just want to finish this part because it's quite difficult to come back to this for another day. Okay, so this part is done. Worker ID thread. So we're doing some error handling here after receive. Receive will be the result. And then we're using match if it's okay. Print job executing, if not error, disconnecting, break. And in main RS, although this is 4, here we're only taking 2. Okay, let's check our main RS. 4, listener incoming, take 2. So we are changing this, coming, take 2, take 2. Okay, taking 2, stream unwrap, execute, closure, handle. Okay, print line shutting down, execute. That is 4 inside of 4 loop. Then here can put shutting down. Okay, almost there, almost done. You wouldn't want a real-world web server to shut down after serving only 2 requests. This code just demonstrates the graceful shutdown and cleanup is in the working order. The take method is defined in the iterator trait and limits the iteration to the first 2 items at most. The thread pool will go out of scope at the end of the main, and the drop implementation will run. Okay, thread pool will go out of scope, and then the drop implementation will run. So out of scope, then the drop in the thread pool will run. So takes the value out of the option. Okay. Then here it will join and shut down. Okay, then we do this cargo run once again. Cargo run. So let's do this. There, shutting down. Nice. Okay, you might see a different ordering of worker IDs and messages printed. We can see how this code works from the messages. Worker instance 0 and 3 got the first two requests. Avatars. The same to 0310. It's not the same. Instances 0 and 3 got the first two requests. 0 and 3 got the first two requests. The server stopped accepting connections after the second connection. And the drop implementation on the thread pool start executing before worker 3 even starts its job. Dropping the sender disconnects all of the worker instances and tells them to shut down. The worker instances each print a message when they disconnect. And then the thread pool calls join to wait for each worker thread to finish. Notice one interesting aspect of this particular execution. The thread pool dropped the sender, and before any worker received an error, we tried to join worker 0. Worker 0 had not yet gotten an error from receive. So the main thread blocking waiting for worker 0 to finish. In the meantime, worker 3 received a job, and then all threads received an error. When worker 0 finished, the main thread waited for the rest of the worker instances to finish. At that point, they had all exited their loops and stopped. Congrats, we now completed our project. We have a basic web server that uses a thread pool to respond asynchronously. We're able to perform a graceful shutdown of the server, which cleans up all the threads in the pool. Here's the full code for reference. Okay, so we've managed to update the code also. We could do more here. If you want to continue enhancing this project, here are some ideas. Add more documentation, add tests to the library, change calls to unwrap, use the thread pool to perform some tasks other than serving web requests, find a thread pool crate on crates.io and implement a similar web server using crate instead. Then compare its API and robustness to the thread pool we implemented. Summary, well done, you've made it to the end of the book. We want to thank you for joining us on this tour of Rust. You're now ready to implement your own Rust projects and help with other people's projects. Keep in mind that there is a welcoming community of other Rust stations who would love to help you with any challenges you encounter on your Rust journey. So, finally, day 40. That completes our journey in Rust. But it feels like there's still a lot of things to learn here. Yeah, so although we have implemented this multi-threaded web server, but it's not like a a real world representation of a real world project also. But it's good that we did this. At least there's some realization that some realizations that we have here. Mainly, okay, to me this part here is already quite complex. Handling options, where we have, where was that? The drain. It's the drain. I think eventually it was replaced also. Yeah, it was also replaced. Worker ID, some thread. Yeah, so it was replaced. Let me check from the code and search for it. Drain. Oops. Drain. Oh, drain is here. Drop. Drain is here. My mistake. Take. Sender take. Okay, sender take. For worker in self workers. Ah, I forgot. It should be removed. Workers. Worker in at mut. Let's just copy this. Then what is wrong with this? Worker thread take, thread join, unwrap. Join handle is not an iterator. Worker, okay, worker. Some thread worker. Join handle. What happened to the join handle? Thread option. Okay. There. What's the other error? Thread. Thread, some thread. Some thread. Okay. Yep. That's it. And then appendix, let's browse through the appendix and see what's in here. Anyway, we have already extended our time, so it's worth going through the appendix and see. Okay, appendix A, the keywords in Rust. This will serve as a cheat sheet. So you have as async, await, break, cons, continue, create, dynamic, else, enum, extern, false, fn. How many are there? It's a long list. Static, self. Oh, there are two self here. Alias for the type you're defining or implementing. Okay, self, method, subject, or current module. Struct, super, trait, true type, union. I think we haven't used this. Save, we haven't used this. Yeah, so many things needs to be researched. Keywords reserved for future use. Okay, so that's good to know that we have the keywords here. Then about operators and symbols. Okay, macro expression. Okay, so if this comes after a word, okay, but if it comes before, it becomes a bitwise logical complement. Okay, so this one not equal, remainder or modulo, arithmetic, remainder, assignment. Okay, the logical and is this. Then what is or? This one is also increment. Decrement. Okay, so function and closure return. We have range. Okay, so this is division. Left shift. Pattern binding. Bitwise. Okay, so pattern alternative. So if it's logical or it's this. Non-operator symbols. Okay, so we have lifetime, we have the apostrophe, byte, closure, ignored. So underscore is ignored. What is this? Path, name. Okay, name space path. Symbols. Okay, here. Macros and attributes. Meta. Comments. Oh, block comments can be like this also. Then parenthesis. Parenthesis is empty tuple. Okay. Curly brackets. The type. Array. Okay, that's good to know. Derivable traits. What's in here? Yeah, I think we have done this. Partial. Well, I think in the guessing game we might have used this. Might have. I need to check again. Partial or was it vectors? Clone and copy. Okay, hash for mapping of value, default or default values. Okay. Useful development tools. Okay, cargo. We have cargo. Okay, Rust fix. cargo build, cargo fix, cargo clippy, okay, ID integration with Rust, okay, so Rust analyzer, okay, so we have this. And then editions, what's in here? Cargo new, active Rust users, new edition brings together incremental changes into an easy to understand package. Okay, so edition guide, complete book about editions that enumerates the differences between editions and explains how to automatically upgrade. Okay, translations of the book. Okay, so it's good that there are translations of the book also. And then how Rust is made and nightly Rust. Stability without stagnation. Nightly beta and stable. Okay. Toolchain, nightly toolchain list. This is for Windows. RFC, request for comments. Oh, it's been a while since I've come across this term, RFC. Anyone can write RFCs to improve Rust. Okay, it's good to know. All right, so that's basically it. So from here onwards, I'm gonna do, maybe I'll look for another book or probably jump into some projects. We're going to do it live once again. And thank you so much for accompanying me in this journey. It was a long journey, I would say 40 days. 40 days, but congratulations if you made it to this day also. And of course, I'll continue working on some videos and hope to see you on the next one. But first, let me thank my supporters.